You probably have an image in your head of what a black hole leads to. A tunnel, a portal, a cosmic drain that pulls matter through to somewhere else, another universe, a white hole on the other side, some far corner of this one. Maybe you got it from a film, maybe from a documentary, maybe from the kind of science content that reaches for wonder by reaching for the dramatic. That image is almost certainly wrong, and the real picture is stranger than the tunnel, more disturbing, more mathematically interesting, and more honest about what we actually know, which is less than most explanations admit. A black hole doesn't lead to somewhere, it leads to a place where the concepts of somewhere and when stop working the way they normally do. It leads to the edge of what physics can currently describe. And right at that edge, the most interesting collision in modern science is happening. Let's go through it properly. First, strip away the mythology and say what a black hole actually is. It's not a hole, not a vacuum cleaner, not empty space. A black hole is a region of space-time, a region where mass has been compressed to the point that the escape velocity exceeds the speed of light. Nothing that enters can get out. Not matter, not radiation, not information. The boundary of that region is the event horizon. And here's the first thing that should surprise you. The event horizon is not a physical surface. There's nothing there. No wall, no membrane, nothing you could detect locally as you passed through it. It's a mathematical boundary in the geometry of space-time. A surface of no return defined entirely by the structure of the gravitational field. From outside, a black hole is characterized by exactly three numbers: mass, spin, and electric charge. That's it. Everything about what fell in, the atoms, the molecules, the quantum states of every particle, is, apparently, gone from the outside description. This is the no-hair theorem. The black hole has no hair, no detailed features reflecting the complexity of what made it, just three numbers. Now, what happens when you cross the event horizon? Locally, nothing. If you were falling into a sufficiently large black hole, you would not feel the moment of crossing. No wall, no temperature spike, no sudden change, just space, and then, past the horizon, a geometry that is subtly different in a way that becomes rapidly catastrophic. Inside the event horizon, space-time is structured so that every path forward, every possible future trajectory, points toward the singularity. Not because of a force pushing you inward, because of geometry. Inside, the radial direction toward the singularity has become time-like. It's not a direction in space anymore, it's a direction in time. You can't stop moving toward the singularity any more than you can stop moving toward the future. It's not a trap you fell into, it's a region of space-time where forward in time means inward toward the center. At the center, general relativity predicts a singularity, a point of infinite density, infinite space-time curvature. The equations produce infinity and then break. I want to say something careful about this because it matters. Physical infinities in the equations of a theory are almost never a signal that infinity actually exists in nature. They're almost always a signal that the theory has been pushed outside the domain where it's valid, that you've reached the edge of the model, not the edge of reality. When you apply Newtonian gravity at zero distance, you get infinite force. We don't conclude that infinite forces exist. We conclude that Newtonian gravity doesn't apply at zero distance. The infinity is the model's way of telling you it's broken. The singularity in general relativity is the same kind of signal. At the scales where the singularity forms, around the Planck length, roughly 10 minus 3/3 meters, quantum effects must become dominant. General relativity, which is a classical theory, has no machinery for quantum effects. It continues grinding out predictions in a regime where it's not equipped to make them. The singularity is where general relativity honestly runs out. What actually happens at the center of a black hole? We don't know. A complete theory of quantum gravity, a theory that correctly unifies quantum mechanics and general relativity, would tell us. We don't have that theory yet. The singularity is not a destination. It's a confession that our description ends. Let me tell you what falling into a black hole is actually like, because it depends on which kind. For a stellar mass black hole, a few to a few dozen times the mass of the Sun, the event horizon is small, and the tidal forces near it are extreme. Tidal forces are the difference in gravitational pull between the near side and the far side of an extended object. Your feet, closer to the singularity, feel stronger gravity than your head. That differential stretches you. And near a stellar mass black hole, this stretching, this spaghettification, would kill you long before you cross the horizon. You'd be drawn out into a thin stream of particles by a force differential that no biological or material structure could survive. For a supermassive black hole, millions or billions of solar masses, like the one at the center of most large galaxies, like the one imaged by the Event Horizon Telescope, the physics is different. The event horizon is vastly larger, and tidal forces at the horizon scale inversely with the black hole's mass. The bigger the hole, the gentler the gradient at the horizon. At the event horizon of a billion solar mass black hole, the tidal forces are mild. You could cross it in free fall without feeling anything unusual, without knowing, in fact, that you'd crossed it at all. The moment of crossing is locally unremarkable. The consequences, however, are absolute. You're inside. Every future path leads inward. Tidal forces will eventually kill you as you continue falling, but the crossing itself, for a large enough black hole, can be gentle. That's deeply counterintuitive. The bigger the black hole, the safer the crossing, in a narrow sense. The danger is delayed, not avoided. Now, the information paradox. This is the problem that tore theoretical physics apart for nearly 50 years, and it's still not fully resolved. Quantum mechanics has a law built into its mathematical foundations. Information cannot be destroyed. The total quantum state of a closed system, the precise description of every particle and its relationships, must be preserved as the system evolves. This is called unitarity. It's not a preference or an approximation. It's a foundational structural feature of quantum theory. General relativity says, what crosses the event horizon stays inside. Nothing comes back out. These two statements are directly, irreconcilably in conflict. In 1974, Stephen Hawking showed that black holes aren't completely black. Due to quantum effects near the event horizon, specifically the way quantum fields behave in curved spacetime, black holes slowly emit radiation, Hawking radiation. The energy comes from the black hole's mass, so over enormous timescales, the black hole evaporates, shrinks, eventually, presumably, disappears. If the Hawking radiation is perfectly thermal, random, carrying no information about what fell in, then when the black hole is gone, the information is gone too. Quantum mechanics is violated. Unitarity is broken. Hawking originally argued this was true. Information is destroyed. He later changed his position. Most physicists today believe the information must escape somehow, encoded in the Hawking radiation. But the how remains contested. This disagreement produced some of the most interesting and most genuinely strange proposals in modern theoretical physics. In 2012, 4 physicists, Amheri, Marolf, Polchinski, and Sully, published a paper that became known simply as the AMPS paper, and what it showed disturbed people. They argued if information really does escape in Hawking radiation, then the radiation emitted late in the evaporation must be entangled with radiation emitted early. That's required for the information to be preserved. But those late emitted particles must also be entangled with particles inside the black hole. That's required for the horizon to be smooth and empty, as general relativity demands. And quantum mechanics has a rule called monogamy of entanglement. A particle can't be fully entangled with two different systems simultaneously. Something has to break. Either the information isn't preserved, quantum mechanics breaks, or the entanglement with the interior is severed, and the horizon is not smooth and empty. Instead, it's a wall of high-energy radiation, a firewall. An infalling observer is incinerated at the horizon, not after it. This directly contradicts general relativity, which predicts a freely falling observer should detect nothing special at the event horizon. So we have either quantum mechanics breaks at the horizon, or general relativity breaks at the horizon. In both cases, something breaks. The two theories, pressed to this precise question, give incompatible answers. String theory offers a different picture. In some formulations, black holes are what are called fuzzballs, quantum objects made entirely of strings, with no smooth interior, no event horizon in the classical sense, no singularity. The interior is a quantum state, not a geometric region. There's nothing to fall into in the traditional sense. The black hole is entirely a quantum mechanical object, and the geometry we normally associate with it is an emergent, approximate description. And then there's the holographic principle. The idea, supported by a remarkable result in string theory called the ADS-CFT correspondence, that all the information in a volume of space is encoded on its boundary surface. Applied to black holes, everything that has ever fallen in is encoded on the event horizon. The interior, in some deep sense, is the event horizon. The question, what's inside, may be like asking, what's behind a hologram? The image is all surface. Maldacena and Susskind proposed something called ER equals EPR. That quantum entanglement between particles and geometric wormholes are the same thing, described in different languages. The Hawking radiation particles, entangled with the interior, might be geometrically connected to the interior via microscopic wormholes. The inside and the outside, linked by entanglement, made spatial. These ideas are serious. They come from the most technically sophisticated corners of theoretical physics, and they disagree with each other about fundamental questions: whether there's an interior at all, whether the horizon is smooth, what the information does. Let me say something about wormholes, because they appear in the mathematics and they deserve an honest treatment. The exact solution to Einstein's equations for a non-rotating black hole, worked out in full by Kruskal and Sekares, contains more than just a black hole and its interior. The complete mathematical solution has four regions: our exterior universe, the black hole interior, a white hole, a time-reversed black hole, where matter is ejected and nothing can enter, and a second exterior region, a second universe, connected to ours through what's called an Einstein-Rosen bridge, a wormhole. Mathematically, it's there. It's in the equations, in the exact solution. Physically, it's almost certainly not there in real black holes. Real black holes form from collapsing matter. The complete eternal Schwarzschild solution describes an idealized eternal black hole that has existed forever, which real ones haven't. The full four-region structure requires conditions that aren't met by astrophysical black holes. And even if a wormhole existed in the mathematical sense, it's non-traversable. It pinches off too quickly for anything to pass through, even at the speed of light. You can't use it to go anywhere. The wormhole in the Schwarzschild solution is a geometric feature of the space-time, with no physical consequence for anything trying to travel through it. Traversable wormholes, the kind that lead somewhere useful, would require exotic matter with negative energy density to hold them open. There's no confirmed evidence for the existence of such matter in the required quantities or configurations. The mathematics permits them under certain conditions. Whether nature provides those conditions is an open and probably deeply unlikely question. The gap between what equations allow and what nature actually instantiates is where a lot of wishful thinking in physics lives. Where does a black hole really lead? Honestly, we don't know. And the question itself may need to be reformulated before it can be answered. The singularity isn't a destination, it's a breakdown of our description. The interior may not be a where in the classical sense at all. If the holographic principle is correct, the interior is the horizon, and asking what's behind it may be a category error, like asking what's north of the North Pole. The information paradox is unresolved. The firewall debate is unresolved. Whether quantum mechanics or general relativity breaks near the horizon is unresolved. Whether there's a classical interior at all in the quantum gravitational sense is unresolved. What black holes have done to physics is worth more than any specific answer they might eventually give. They found the exact seam between the two greatest theories in physics, quantum mechanics and general relativity, and pulled it apart precisely enough that the incompatibility is undeniable. They've given us a laboratory, not in space, but in mathematics, where the next theory of physics has to work. Whatever comes after general relativity and quantum mechanics, it has to handle black holes correctly. Dirac spent his career believing that when equations are beautiful, they're pointing at something true. The mathematics of black holes is extraordinarily beautiful. The Penrose diagrams, the topology of space-time, the elegant horror of the information paradox. There's a structural elegance to all of it that suggests the real answer, when found, will be something we'll recognize as mathematically inevitable. But we don't have it yet. The language that describes what actually happens inside hasn't been written. A black hole is the place where space-time curves so severely that everything, matter, light, information, and eventually our best theories, falls inward without return. The question of what waits at the bottom of that fall is the next frontier, the next place where physics has to go. And we don't know what it looks like yet, which means we're at the best possible place to be, right at the edge.